Last week we covered two different chapters, resistive inductive series circuits and resistive inductive parallel circuits. This is homework review for the series circuits. This is based out of the 6th edition, and let's cover them now. Number 1, what is the relationship of voltage and current concerning phase angle in a pure resistive circuit? So this is a purely resistive circuit. And the answer is the voltage and current are in phase with each other. Number 2, what's the relationship concerning phase angle in a pure inductive circuit? In a pure inductive circuit, the current and voltage are 90 degrees out of phase. Number 3, what is power factor? Power factor is the ratio of true power to apparent power. That's the answer to the question. A couple of notes here. Power factor is generally expressed as a percentage, and we cannot use current to calculate power factor because current is the same in series circuits. For number 4, we have a circuit, AC power source. It's a series circuit with a resistor and an inductor, 20 ohm resistor, a 93 millihenry inductor, and we have 60 hertz. And the question is asking, what is the total impedance of the circuit? Impedance is Z here. So to solve for impedance, we need the resistance, and we also need the inductive reactance of this inductor. Inductive reactance, again, is the current limiting thing of an inductor. That formula is shown here. I'm just going to rewrite it. And if we substitute in our known values, we get an inductive reactance of 35 ohms. Now we can solve for impedance. Impedance is the square root of R squared plus X sub L squared equals square root of 20 squared plus 35.061 squared, and that equals 40.36 ohms. Number 6. A resistive inductive series circuit has an apparent power of 230 volt amps and a true power of 180 watts. What is the reactive power? That formula is shown here. I'm going to rewrite it for clarity. Equals the square root of VA apparent power squared minus true power squared equals the square root of 230 volt amps squared minus 180 watts squared, and that equals 143.18 bars. That's shown right here. Number 7, the resistor in a resistive inductive series circuit has a voltage drop of 53 volts, and the inductor has a voltage drop of 28 volts. What is the applied voltage of the circuit? This formula is in Appendix B in either textbook, and that formula I'm going to rewrite. Total voltage equals the square root of the voltage drop across the resistor squared plus the voltage drop across the inductor squared equals the square root of 53 squared plus 28 squared equals 59.94 volts. Number 9, a resistive inductive series circuit contains a resistor and an inductor. The resistor has a value of 6.5 ohms. The circuit is connected to 120 volts and has a current flow of 12 amps. What is the inductive reactance of this circuit? Two-step process, and these formula are again in Appendix B in either textbook, either edition. So first, solving for impedance, it's the applied voltage over the circuit current, and that gives 10 ohms. Next, we solve for inductive reactance. That is the square root of impedance squared minus resistance squared equals the square root of 10 squared minus 6.5 squared equals 7.6 ohms for inductive reactance. Number 10, what is the voltage drop across the resistor in the previous question? And that's Ohm's law. I'll rewrite it here. Voltage drop across the resistor equals the current through the resistor times the resistance of the resistor equals 12 amps times 6.5 ohms equals 78 volts. And finally, number 12. A resistive inductive series circuit has a power factor of 73%. If the apparent power is 560 kilovolt amps, what is the true power of the circuit? That formula again is in Appendix B. True power equals power factor times apparent power equals 0.73. When we have the power factor in percentage, we need to convert it to the decimal form for calculations. So 73% equals 0.73. That's where this comes from. Times the apparent power. That's 560,000 because it's kilovolt amps. And the answer is 408,800 watts equals 408.8 kilowatts.